Welcome back. We have a fascinating stack of sources today, and they're really custom tailored for you if you're deep in your aviation maintenance technician general course right now.
That's right. You're building that foundation.
Exactly. And honestly, nothing's more foundational than learning the technical language, the visual language used to communicate design and maintenance across, well, every major airframe out there.
It has to be precise. The language of aviation maintenance, I mean,
Yeah.
the stakes are just incredibly high.
No room for error.
None. And our sources really hammer this point home. Just relying on written words or even spoken instructions, it inevitably leads to misunderstandings, dangerous ones.
Yeah, I can see that. Like a misplaced comma.
Or just one ambiguous word, it can completely flip the meaning of a critical instruction.
And that's where this draftsman's language comes in, right? The aircraft drawing.
Precisely. It's a standardized system. It uses this universally understood set of lines, notes, abbreviations, symbols, all designed specifically to kill that ambiguity.
So if you have to build it or fix it or inspect it,
The drawing is your guide, your error-proof guide.
that's really the mission for us today, isn't it? We want to help you move past seeing these blueprints or, these digital diagrams as just complicated geometry homework.
Right. You need to see them as navigational charts, as a set of instructions that translates directly into physical action. A wrench in your hand, a drill, whatever the tool.
And it's not just old paper blueprints anymore, is it? I mean, the industry's leaped forward.
Oh, massively.
No.
And the language of drawing, it's adapted. It had to. It's adapted to digital speed, three-dimensional visualization. It's a whole new world in some ways.
But the core principles remain.
The core principles of clarity and precision, yes, but understanding how we got from paper to pixel, that digital evolution, that context, is just as critical as understanding, say, the coordinate system of the airframe itself.
Okay, let's unpack that then. Let's start with this modern evolution of aircraft documentation. So for most of aviation history, the 20th century certainly, drawings were a very manual process.
Absolutely. On a drawing board, pencil or pen, big sheets of paper. Slow work.
Time-consuming and, I imagine, prone to little manual errors. Things that needed careful checking.
Exactly. Laborious cross-checking was essential, but then computers arrived. Late 20th century.
And that changed everything.
Dramatically.
Yeah.
It wasn't just about drafting faster, though it did that too. It completely revolutionized design validation.
How so?
Well, with computers, engineers could suddenly display items in, well, virtual reality, essentially. They could look at a component from any conceivable angle.
Okay, that's useful.
But the real game changer wasn't just viewing, it was virtual assembly. Engineers could take parts designed separately and digitally assemble them, a virtual mock-up.
Ah, so they could check the fit.
Check the fit, yes, but crucially, identify potential interferences before anything physical was ever made.
Right. Finding out a hydraulic line clashes with a structural rib after you've made the parts. That sounds expensive.
Hugely expensive. And causes massive delays. Computers let you find and fix those clashes in the digital world, saving enormous amounts of time and money.
So this integration of design, drafting, analysis. This leads us to all those acronyms, right? The ones every AMT student starts hearing.
That's the soup. And they aren't just academic terms. They define the tools, the processes that actually created the aircraft you're training to maintain.
Okay, let's break them down. The foundation is just computer graphics, right? Simply drawing with the computer.
Simple concept, powerful tool. From there, you build systems. CAD, computer-aided design.
That's the creative part, geometry, structure.
Exactly. The design phase,
Yeah.
performance characteristics, all that. Add the drafting element, the creation of the actual drawings from the design.
And you get CAD, computer-aided design drafting.
Got it. And then the process extends downstream, linking that design to actually making the part.
Which is CAM, computer-aided manufacturing.
Right. The computer translates the design data directly into instructions for the manufacturing equipment. Automated milling machines, 3D printers, ensures incredible precision.
Okay. CAD, CANI, CM. What's the last one?
The big umbrella, really, and maybe most relevant for the future AMT, is CAE, Computer-Aided Engineering.
So that covers everything.
It uses the computer throughout the entire engineering process. Product analysis, simulating assemblies, stress tests, and importantly for you, creating the detailed maintenance and instructional data.
Okay, so the key takeaway here for the student is
Okay.
what? that these systems are fast.
Speed is part of it, yes. But the bigger implication is continuous refinement. Designs evolve quickly with CAE. So your primary job isn't just interpreting some static drawing from 1985.
It's making sure the digital version you're looking at on your tablet or laptop
Is the absolute current version. Before you touch anything on that aircraft, configuration control is paramount.
and specific software drives this.
Oh, yes. Sophisticated packages. The sources mention CATIA, that's the big one, used by most major airframe manufacturers to design entire aircraft. Complex surfaces, structure, everything.
Any others?
Pro Engineer, SolidWorks, Unigraphics, they're all key players in the industry.
And what does this mean for the technician on the hangar floor?
Unprecedented accessibility. Drawings aren't stuck on paper anymore, limited to 1, 2, maybe 3 views.
You can pull up detailed drawings, manuals, even interactive 3D models on a laptop or rugged tablet right there next to the component.
Exactly. The manufacturer often designs and virtually assembles the entire aircraft before a single rivet is bucked. And that complete 3D data set is increasingly what you're referencing.
It's a different world. But just for context, how did they make those old hard copies? The blueprints.
Right. The historical context is useful. The original prints, the actual blueprints, were made by tracing the original drawing on semi-transparent paper over chemically treated paper.
And then exposing it to light.
Strong light, yes. The chemical reaction created the image, typically white lines on a distinctive blue background, though other color combinations existed too.
And nowadays, if you do need a hard copy,
Standard inkjet or laser printers for smaller stuff, but for the really big structural drawings,
you need something bigger.
large format plotters. These things can handle paper up to, say, 42 inches high and sometimes continuous rolls hundreds of inches long, necessary for showing major fuselage sections full scale.
Okay, stepping back a bit. Fundamentally, why do drawings exist? They're the bridge, right?
The link between the engineers designing the thing and the people actually building, maintaining, or repairing it.
Exactly. And to be effective, they must convey specific information. Size, shape, material, finish, how it all goes together.
So to use them correctly, you first need to know what kind of information you're even looking at. What's the scope?
And that scope is defined by 3 essential classes, or types of drawings. Let's start small. The detail drawing.
Okay, detail sounds like a single part. Precisely. It describes one individual component. It's the most specific instruction set for that single piece. Size, shape, material, how to manufacture it.
So like a specific bracket
Yeah.
or a rivet.
Perfect examples. They're often simple. So simple, in fact, that you might find several small detail drawings grouped together on a single sheet of paper. Think of it as the recipe for making that one specific piece, maybe in the sheet metal shop.
Got it. So from a single part, we zoom out to
The assembly drawing. This describes an object that's made up of 2 or more of those detailed parts.
okay, so it shows how they fit together.
That's its primary purpose, to show the relationship between the various components, how they connect, how they're fastened, maybe the sequence of assembly.
How is that useful for maintenance?
It's vital. Assembly drawings often use item numbers, maybe in little circles or squares that point to the individual parts.
And those numbers link back to the detailed drawings or something else.
They link back to the detail drawings and to the bill of material, which we'll talk about later. So it shows how Part A mates with Part B, but, and this is key, it doesn't necessarily show you where that completed assembly goes on the aircraft.
Ah, okay. So for that, you need the third type.
Exactly. The largest scope. The installation drawing. This one includes all the necessary info for putting a part or a completed assembly into its final installed position on the aircraft.
This sounds like the main one for maintenance techs.
It's crucial, yes, because it shows the location, the attachment points, all relative to the airframe structure. It gives you the context.
So give me an example. Installing a new antenna.
Perfect. The detail drawing tells you how the antenna base is made. The assembly drawing shows how the base, the gasket, and the antenna mast fit together. But the installation drawing...
That tells you where on the fuselage it goes.
Exactly. Often referencing specific coordinates like water lines or fuselage stations, which we'll also get to. It shows its position relative to everything else around it.
Okay, 3 classes. Detail, assembly, installation. Got it. Now, sometimes you need to see inside a part, right? Especially complex ones.
Absolutely. And that's the job of sectional views. You create them by imagining you've cut away a portion of the object.
To show the interior shape, the construction.
Precisely. And the parts that are cut by this imaginary plane are always marked with specific patterns called cross-hatching lines.
Are there different types of cuts?
4 main types you need to know. First is the full section. This is used when the inside is complex or has hidden features you just can't show clearly from the outside.
Like what?
The source uses a great example: the internal construction of an electrical cable connector. If you just drew the outside, you'd have no idea how the pins, the shielding, the locking bits are arranged inside. A full section cuts right through it.
Makes sense. What's next?
Half section. Here, the imaginary cutting plane only goes halfway across the object.
Why only halfway?
It's used for symmetrical objects. By cutting only halfway, one side of the drawing shows the internal construction.
And the other side shows the normal exterior view.
Exactly. It's efficient, saves drawing space, and lets you easily compare the inside and outside. The example given is a capstan servo, which is often symmetrical.
Okay, full and half. What else?
The next two are about showing the shape of a cross-section. You have the revolved section. This is drawn directly on the exterior view.
On it. How does that work?
It looks like you sliced the object right there and then rotated that cross-section 90 degrees in place. It's used to quickly show the shape of a specific feature.
Like the T-shape of a spoke on a wheel.
Perfect. Or the profile of a small stiffener. It clarifies the shape without needing a whole separate view.
But what if that revolved section is too small to see clearly? Or needs really precise dimensions?
Then you use the fourth type, the remove section. It's just like a revolved section in what it shows the cross-sectional shape, but instead of being drawn on the main view.
It's placed off to the side.
Exactly. Placed elsewhere on the drawing, often drawn to a larger scale to really highlight the important details or dimensions. And it's clearly labeled, maybe section AA or section BB, corresponding to cutting plane lines on the main view. Okay, so we know the types of drawings, how to show internal views. Now let's talk about the fundamental way we represent 3D objects on 2D paper or screens. The vast majority of engineering drawings use orthographic projection.
Why orthographic? What's special about it?
Its primary job is accuracy. It conveys the exact size and shape of the component without the distortion you get in, say, a photograph.
How does it achieve that? I remember something about a box.
The transparent box concept, yes. Imagine placing the object inside a clear cube. You look straight at each face of the cube front, top, bottom, rear, right, left, and trace the outline of the object onto that face.
All right.
Then you mentally unfold the box. The resulting 6 views, laid out flat, form a complete 6-view orthographic projection.
Do aircraft drawings usually show all 6 views? Seems like a lot.
Rarely. It's almost never necessary. You only draw the minimum number of views required to fully define and dimension the part.
So usually fewer than 6.
Much fewer. 1, 2, or 3 view drawings are the most common. And they're always arranged in a standard way relative to the main view, the front view, often called the principal view.
Can you get away with just one view sometimes?
Yes, for simple things. Objects with uniform thickness, like a gasket or a flat plate. The thickness can just be stated in a note. Or for perfectly cylindrical or spherical parts where one view, plus dimensions, tells the whole story.
What about complex aircraft parts?
Typically, you'll see one main complete view, and then it'll be supported by one or more detail views or sectional views to clarify specific areas.
Detail views, we mentioned those briefly. The zoom-in function.
Exactly. Think of it as the magnifying glass on the drawing. It shows only a small part of the object from the main view.
But bigger. And with more detail.
Yes, always in greater detail and critically drawn to a larger scale than the principal view. This lets the draftsman add dimensions or notes that wouldn't fit on the main view.
And how do you know which part is being magnified?
There's usually a heavy, often circular line enclosing that specific area on the principal view, and it'll be labeled like C detail A, pointing you to the separate, larger view elsewhere on the drawing. If you're struggling to read a tiny radius dimension, look for that circle.
Okay, orthographic is for precision. What about just showing what the thing looks like?
For that, we use pictorial drawings. These show the object more like how our eyes see it in 3 dimensions.
More like a photo.
Some are, yes. They're incredibly useful for getting a general feel for appearance and how parts relate spatially. You see them everywhere in maintenance manuals.
Are there different types of pictorial drawings, too?
4 key types to know. First is perspective. This one looks the most realistic, very much like a photograph. Lines converge towards vanishing points.
Sounds great for visualizing.
It is, but there's a huge warning for you as a technician. Because of that perspective effect, the lines are not parallel, and the angles and dimensions shown are not accurate. You use perspective for general understanding, never for measurement.
Okay, so what can you measure from?
That's where the isometric drawing comes in. It also shows the object tilted, so you see parts of three views at once, giving it a 3D look.
But the lines.
The lines remain parallel, and crucially, dimensions drawn along those main isometric axes are true and accurate. It gives you that 3D feel with measurable data. Very useful for figuring out how things orient before you install them.
Got it. Isometric for measurable 3D. What's the third type?
Oblique drawing. It's similar to isometric in showing depth, but it's constructed differently. One face of the object is drawn true shape, parallel to the drawing plane, and the depth lines recede at an angle, usually 45 degrees.
When would you use that?
Often when one face of the object is the most important or has complex features you want to show head-on without distortion, while still giving a sense of depth.
Okay. Perspective. Isometric. Oblique. What's the last one? This one sounds important for parts.
Absolutely critical for parts ordering and assembly. The exploded view.
Ah, I've seen those, where the parts are kind of floating apart.
Exactly. It shows two or more parts that fit together, but they're drawn slightly separated along common center lines, showing their relative positions before assembly.
So you can see the order they go in.
Precisely.
Yeah.
And usually they have those little item numbers pointing to each part. They are indispensable for finding the right part number in the illustrated parts catalogs, the IPCs.
And for figuring out how to put something back together using the maintenance instruction manuals, the MIMs.
Couldn't do the job without them sometimes.
Okay, so you've got a drawing in front of you, maybe on a screen, maybe paper. Before you even try to interpret the lines and views, you need to authenticate it, verify it.
Absolutely. You start with the title block. It's the ID card for every single print. Usually you'll find it tucked away in the lower right-hand corner.
And it's packed with info.
Essential data. Our sources list 7 key things you'll always find there. First, the unique drawing number. Second, the name of the part or assembly. Third, the scale of the drawing. Is it full size, 1.1, half size, 1.2, etc.
Okay, number, name, scale, what else?
The date it was originally drawn, the name of the firm or company, and then the accountability trail. The names or initials of the draftsman who drew it, the checker who reviewed it, and the approver who signed off on it.
As a technician, are the names that important, or is it more about the number and revisions?
For you, the drawing number is critical for finding the right print, and even more critical is checking the revision block. But the numbering system itself is designed for quick ID. Often the number appears elsewhere too, maybe on the top border or printed in reverse so it's readable even when the print is folded up in a drawer.
What if one drawing needs multiple pages?
The title block area will indicate that too. It'll say sheet 1 of 3 or similar.
Okay, back to that revision block. You said it's crucial. Why?
Because aircraft designs change, parts get updated, materials change, dimensions are tweaked. The revision block, usually located near the title block, lists every single change made to that drawing since it was first released.
And it details the change.
Yes, it has an identification symbol, usually a letter, the date the change was made, a brief description of the revision, the authority for the change, like an engineering order number, and who made it.
And the danger is using an old revision.
It's probably the single most common cause of major maintenance errors. Using a drawing that isn't the latest approved revision, you must cross-reference the revision letter on the drawing with the requirements in the current approved maintenance manual or service bulletin, no exceptions.
Got it. Check the revision. What about other numbers in the title block area? Reference and dash numbers.
Right. Reference numbers are like pointers. They direct you to other drawing numbers that are related, maybe drawings needed to complete the assembly shown.
And dash numbers.
Dash numbers are used to distinguish different versions or variations of a part shown on the same drawing number. So drawing 40267 might show a basic bracket, but 402671 is a slightly modified version, and 402672 is another variation, maybe drilled differently.
Okay. And they're also used for left and right parts.
Very commonly. To save drawing effort, the print might only fully illustrate the left-hand LH version of a part.
And then a note says the right-hand RH version is just the mirror image.
Exactly. It'll say RH opposite shown or something similar. The dash number often distinguishes them. Maybe Manic 1 is LH and Manicus 2 is RH. Or sometimes they use odd numbers for LH and even for RH. You have to read the note carefully to make sure you're ordering or installing the correct mirrored part.
There's also something about a universal numbering system for drawing size, like A, B, C, D, E.
Yes, it's a standard code just identifying the physical size of the paper the drawing was originally intended for. A size is your standard 8.5 by 11 inches, like letter paper. E size is much larger, maybe 34 by 44 inches.
Why does a technician need to care about the paper size, especially now with digital viewers?
It's a quick indicator of scope and complexity, even digitally. If you see it's designated A size, you can bet it's probably a detailed drawing of a pretty small, simple part.
Whereas an E-size drawing.
That's almost certainly a large, complex assembly or installation drawing, maybe showing an entire wing spar or fuselage section. It mentally prepares you for the level of detail you're about to encounter.
Okay, moving off the drawing itself and onto the actual aircraft, how do drawings pinpoint where something is located?
Through a standardized 3D coordinate system,
Yeah.
aircraft location identification, absolutely vital for structural repairs, component installation, everything.
Based on reference points.
3 main references. First, forward and aft location is measured by fuselage stations, or FS.
Stations like inches from the front.
Exactly. Measured in inches aft from a defined 0 point called the datum. The datum is often the tip of the nose or maybe the front face of the firewall. So FS 185 means a point exactly 185 inches aft of that aircraft's 0 datum point.
Okay. Forward and aft is FS. What about side to side?
That's the buttock line, or BL. It measures the distance in inches left or right of the aircraft's longitudinal center line. So you'll see references like LBL 50 inches left of center, or RBL 100 inches right of center.
In up and down.
That's the waterline, or WL. It measures the vertical distance in inches from a defined horizontal reference plane.
So FS, BL, and WL give you a precise 3D coordinate for any point on the airframe.
Any point. Fixed structural coordinates.
Now, quick question. What if the aircraft isn't sitting level? Say it's on jacks, maybe one wing is high. Does the waterline measurement change relative to the floor?
Excellent question. And the answer is no, it absolutely does not. That's the whole point.
They're fixed to the structure.
Exactly. FS, BL, and WL are coordinates relative to the aircraft's internal structure, defined by the manufacturer. They are completely independent of the aircraft's attitude relative to the ground or the hangar floor. Whether it's flying, taxiing, or jacked up at a weird angle, FS 185, RBL 50, WL 200 is always the exact same physical point on that airframe structure.
That makes sense. Crucial for repairs.
Yeah.
Okay, let's talk manufacturing precision. Allowances and tolerances.
Right. No part can be made to an exact dimension every time. There's always some variation. The allowance is how much variation is permitted. It's the plus or minus figure you see next to a dimension.
And the tolerances.
Simply the total range of acceptable variation. It's the difference between the maximum and minimum acceptable dimension. So it's the sum of the plus allowance and the minus allowance magnitude.
The source example is 0.225 inches with allowance of plus 0.00025 and minus 0.0005.
Notice that it's asymmetrical. The allowed oversize is larger than the allowed undersize.
Does that mean something?
Often, yes. It might tell you something about the required fit. Maybe it needs to be tight going in one direction, smaller, but has more room to be slightly larger.
So for that example, the largest acceptable size is 0.2275 inches.
0.225 plus 0.00025.
And the smallest is 0.2245 inches.
0.225, 0.00005.
So the total tolerance, the total acceptable range, is 0.00030 inches.
Precisely. And you'll notice dimensions needing this kind of precision are always given in decimals. Fractions are reserved for less critical dimensions where more variation is acceptable.
What if there's no specific tolerance listed next to a dimension?
Then you look for the general print tolerance, usually stated somewhere in the title block area. It might say something like all fractional dimensions 132 inch, or all 3 place decimals bring 1.005 inches. That's your default, unless specified otherwise.
Okay. What other data blocks are essential?
The bill of material.
The BOM. Absolutely vital. It's basically the shopping list for the drawing.
It lists all the parts needed. All materials and parts required to make the assembly shown on the drawing. It includes the part number for each item, its name, the required material, the quantity needed for one assembly, and sometimes the source or vendor, key for ordering spares.
And how do you connect the drawing to the BOMA?
On assembly drawings, you'll see those item numbers we mentioned earlier, often in circles or squares, with leader lines pointing to the specific components on the drawing itself.
So you find the bolt on the drawing, see its item #5.
Then you go to the BOM, find item #5, and get the exact part number, material spec, and maybe even the required torque value right there.
Makes sense. What about notes? Drawings seem to have a lot of notes.
They do. Notes are used whenever information can't be conveyed clearly or efficiently using just lines and symbols, or if it would clutter the drawing too much.
Like a kind of info.
Specific instructions on assembly methods, alternative parts you could use, modifications required, finished specifications like painting or plating, lots of things. They're usually grouped together and numbered consecutively. If a note applies to a specific area, an arrow will point right to it.
Okay. Last block. Zone numbers. Sounds like map coordinates.
That's exactly what they are. On large, complex drawings, like those E-size sheets, the borders are marked with letters along one edge and numbers along the adjacent edge.
Like a grid. A, B, C, and 1, 2, 3.
Precisely. So if a maintenance instruction or maybe another drawing tells you to see detail in zone C4, you can quickly find that intersection on the grid.
Instead of scanning the entire massive drawing looking for it.
Saves a huge amount of time, especially on complex installation drawings.
All right, we've covered the language for showing parts, assemblies, and where they go. But what about how things work? The systems.
That's where diagrams come in. We shift focus from static components to dynamic function. Diagrams are absolutely essential for troubleshooting aircraft systems.
So a diagram is different from a drawing.
Generally, yes. A drawing usually focuses on the physical construction of parts. A diagram is more schematic. It's a graphic representation showing the various parts of a system and illustrating the methods or principles of its operation.
And just like drawings, there are different types of diagrams.
Several important types the AMT student must be able to distinguish. Using the wrong one for the task will definitely waste time, especially during troubleshooting.
Okay, what's the first type?
Let's start with the installation diagram. As the name implies, its main job is to identify components and show their actual physical location within the aircraft.
Like the installation drawing, but maybe simpler.
Often simpler, yes. It might just show outlines of components in their installed positions with numbers keyed to a parts list. The source example shows flight guidance control components in the flight deck. It's a map to help you find the boxes.
Okay, so installation diagram, location. What's next?
Fundamentally different is the schematic diagram. This one's purpose is to show the principle of operation of a system.
How it works, not where it is.
Exactly. Components are drawn relative to their function within the system. Their actual size, shape, or physical location on the aircraft is usually ignored on a schematic.
So on a schematic for, say, the air conditioning system.
You might see the engine bleed air valve drawn right next to the air conditioning packet feeds, even though physically they might be separated by many feet of ducting in different zones of the aircraft.
Because the schematic only cares about the flow. Bleed air, hydraulic fluid, electricity.
Precisely. It's focused purely on function and flow. Lines are often coded to represent different pressures or signal types. This is the primary diagram you'll use for troubleshooting why a system isn't working correctly.
Got it. Schematic function. What else?
The block diagram. This is the high-level overview, the simplified picture.
How simplified?
Individual components or even entire subsystems are just drawn as simple rectangles blocks. Lines connect the blocks to show the main interfaces and signal flows between them during operation.
So if I wanted to understand how the autopilot computer talks to the navigation system and the flight controls, but without seeing every single wire.
You'd look at the block diagram first. It gives you the big picture relationship between the major players in a complex system.
Okay. And then for the wires themselves.
For that, you need the wiring diagram. Absolutely essential for avionics technicians or anyone doing electrical work.
It shows all the electrical circuits.
Every wire, every connection. It shows the electrical wiring and circuitry, coded for identification wire numbers, colors, gauge sizes, connection points for all the electrical devices in a system or subsystem. Indispensable for diagnosing shorts, opens, or installing new electrical components.
Makes sense. Installation, schematic, block, wiring.
Uh-huh.
Are there other diagram types? What about for decision making?
Yes, flowcharts. We have troubleshooting flowcharts, which are very common in maintenance manuals for tracking down faulty components.
How do they work?
They use standard shapes diamonds for decisions, rectangles for actions to guide you through a logical sequence. They typically consist of a series of yes-no questions.
Leading you down a path.
Exactly. Based on your answer to each question, is the pressure above 50 psi? Does the light illuminate? The chart directs you to the next step, eventually leading to a recommended course of action or identifying the likely failed component.
The source mentions an example for composite repair.
Right. Damage detected, yes. Is it within temporary repair limits? Yes, no. If no, path leads to scrap component. If yes, next question, is a permanent repair kit available? And so on. It ensures you follow a consistent, approved diagnostic logic.
Okay. And there's one more flowchart type mentioned. Logic flowchart.
Yes, these are specifically for analyzing digitally controlled systems. Think autopilots, FAA, full authority digital engine controls, flight control computers.
The brains of the operation.
Exactly. Logic flowcharts use standardized symbols representing logic gates, AND gates, OR gates, not T gates, etc. and they track the flow of binary information, the ones and zeros, the voltage or no voltage states.
To show how the computer makes decisions.
Precisely. They help technicians understand how the digital system should process inputs and determine the correct outputs based on its programmed logic, essential for diagnosing problems in complex digital avionics.
Okay, we've talked about different drawing types, views, diagrams, but ultimately they're all made of lines, right?
Fundamentally, yes, every drawing is just a collection of lines. But, and this is critical, if all those lines look the same.
It would be chaos, a meaningless jumble.
Exactly. The meaning of a line depends entirely on its thickness, its weight or intensity, and its pattern is its solid, dashed dots and dashes. Line standardization is absolutely paramount.
The sources mention 3 basic widths.
Thin, medium, and thick. That variation in width helps your eye distinguish the importance and function of different lines immediately.
So let's break down the main alphabet of lines. What are some key ones?
Okay, first, center lines. You see these a lot. They use an alternating pattern of long and short dashes,
And then they mark.
the center of an object or a feature, the axis of a whole, the center of a symmetrical part.
Got it. What about the lines used for dimensions?
Those are dimension lines. They're typically light, solid lines. They're broken in the middle so the actual measurement figure can be inserted.
And they have arrowheads.
Always. Arrowheads at each end, pointing to the extent of the dimension being shown. And remember, the dimension value itself is always oriented to be read from the bottom or the right side of the drawing.
How do the dimension lines connect to the object?
Using extension lines. These are also thin, solid lines. They extend out from the edge of the object or feature being dimensioned, providing a clear space for the dimension line itself.
Do they touch the object line?
Critically, no. There's always a small, visible gap where the extension line starts, near the object outline. This prevents you from confusing the extension line with the actual edge of the part.
Okay. Center, dimension, extension. What about lines for things you can't see from the outside?
Those are hidden lines. Very important. They consist of a series of short, evenly spaced dashes,
And they represent.
edges, contours, or features that are physically there on the object but are hidden from view in that particular projection. Maybe the inside edge of a hole or a feature on the backside.
And confusing a hidden line with a visible line?
Yeah.
That could be bad.
Very bad. You might try to drill a hole based on a hidden line, thinking it's on the surface you're looking at when it's actually inside or on the back.
Yeah.
Always cross-reference other views to understand hidden lines.
Okay. Hidden lines are short dashes. What about phantom lines? They sound mysterious.
They have a unique pattern. One long dash followed by 2 short, evenly spaced dashes, then repeat. Long, short, short, long.
And what do they indicate?
2 main things. 1, the alternate position of a moving part, like showing a landing gear door in both the closed solid outline and open phantom line positions.
Or a flap.
Or a flap, exactly. The second use is to show the relative position of an adjacent part that's not the main subject of the drawing, but helps provide context.
I see. What's the main line? The one showing the actual edges you can see.
That's the outline or visible line. It's typically a medium to wide, solid line. It represents all the edges and surfaces that are directly visible in that view. It's the primary line defining the shape.
And lines for showing breaks, if a part is too long to fit.
Break lines. For showing a small break in an object, maybe to reveal something inside, you use a thick, freehand wavy line. For breaking out a section of a very long uniform part, like a pipe or shaft, you use thin, ruled lines with zigzags connecting them. Just indicates a portion isn't shown to save space.
Last one. The line that shows where section view was taken.
The cutting plane line. This one's usually extra thick, heavier than the visible outlines. It shows the exact path of that imaginary cut used to create a sectional view.
And it has letters, like A.
Always. Marked with letters at each end, like A, B, B, etc., with arrows pointing in the direction you're supposed to look to see that sectional view. That label corresponds to the label on the actual removed or full section view elsewhere.
Okay, that's the alphabet of lines. What about symbols? You mentioned drawings use shorthand symbols too.
Absolutely. Symbols are graphical shorthand. They let draftsmen portray complex components or characteristics quickly with maximum clarity and minimum drawing effort. Saves tons of time.
What kinds of symbols are common? Material types.
Yes, material symbols. When you look at a sectional view, the pattern of the cross-hatching lines can indicate the general type of material that was cut. There are standard patterns for cast iron, steel, aluminum, rubber, wood, etc.
So you can tell the material just from the pattern.
You can tell the general class of material. However, there's a key point here from the sources.
Oh.
If the exact material specification is already clearly called out in the bill of material or in a specific note on the drawing.
Then the pattern doesn't matter as much.
Exactly. In those cases, draftsmen often just use the standard symbol for cast iron evenly spaced diagonal lines as a sort of generic catch-all pattern for any cut section, simply to indicate this area was cut. The definitive material info is in the bonhomme or the note, so always check those two.
Good tip. What about symbols for shape?
Shape symbols. These are used often within notes or alongside dimensions to clarify the cross-sectional shape of a part, especially for standard structural shapes. Symbols exist for square, round, tubular, showing wall thickness, I-beam, channel, angle iron profiles, etc.
Okay. And the last big category must be electrical.
Definitely. Electrical symbols dominate schematic and wiring diagrams. They're standardized graphic representations for all sorts of electrical devices.
Instead of drawing a picture of a relay.
Right. You use the standard symbol for a relay or a switch, a motor, a fuse, a circuit breaker, a resistor, a capacitor. There are hundreds of them. Mastering these is absolutely fundamental for anyone working with aircraft, electrical, or avionics systems.
Okay, we know the theory now, the lines, the views, the symbols, the data blocks. But knowing the alphabet isn't the same as reading the book. How does an AMT student develop the practical skill of interpreting these drawings correctly?
It comes down to following a systematic procedure every single time. You can't just glance at it. This avoids errors, potentially very costly ones.
So step one.
Always.
Always, always, always. Read the title block. First thing. Verify the drawing number against your work order or manual. Check the part description. Are you looking at the right component? Check the aircraft model applicability. And say it with me.
Check the latest revision letter.
Check the revision letter. If it doesn't match what the current approved maintenance documentation requires, stop right there. Find the correct drawing revision before proceeding.
Okay, title block verified, revision is good. What's step 2?
Get the big picture. Just scan all the views provided quickly. Don't get bogged down in details yet. Just try to grasp the overall shape and general complexity of the object. Form a mental image.
Step 3. This sounds like where the real work begins. It is. Conduct a detailed study. Now you pick one view, usually the principal or front view, and you carefully start relating it to the adjacent views. Top view relates to front view relates to side view. You trace features from one view to the next to understand what each line truly represents in 3D space.
You absolutely cannot just look at one view in isolation if multiple views are provided.
Never. That leads directly to misinterpretation, which brings us to that classic trap the source highlights. Figure 430, the case of the simple circle.
Right. Explain that. So I'm looking at a top view, maybe of an aircraft rib, and I see 2 circles drawn on it.
Looks simple enough. Your first assumption might be, okay, 2 holes need to be drilled here.
So I grab my drill.
Whoa, hold on. Before you drill, what must you do?
Check the other views, the front view or the side view.
Exactly. You look at the side view corresponding to those circles, and you might find that the hidden lines or maybe dimension notes on that side view tell a very different story. Like, the left circle corresponds to hidden lines showing it is a through hole, maybe 14-inch diameter. But the right circle, the side view, might show solid lines indicating it's actually a raised boss projecting up from the surface. Or maybe it corresponds to hidden lines showing a blind hole, one that only goes partway through the material.
And if I drilled through that boss, or drilled all the way through the blind hole,
You've potentially destroyed the part, created scrap, violated structural integrity. That simple act of cross-referencing the views prevents that expensive mistake. Never assume what a feature is from a single view.
Okay, so cross-reference views carefully. Step 4 is dimensions.
Determine size. Now you read the actual dimensions and tolerances carefully. Note if they're using fractions, usually less critical, or decimals, high accuracy required.
Pay attention to the units inches, millimeters.
Absolutely. And note how the tolerance is shown. Is it a plus-minus figure, like per Felici 0.005, or is it given as limits, like 2.01 stacked above 1.99, meaning anything between those two values is acceptable? Read carefully before you measure or machine anything.
So that's reading prints. What about creating them? Do technicians need to draw?
Not formal engineering drawings, usually, but you absolutely need to be able to make clear, effective sketches.
Why would I need to sketch?
Lots of reasons. Maybe you're proposing a modification or a repair method. Maybe you need to document damage found during an inspection so engineering can evaluate it. Maybe you need to quickly convey an idea for a simple tool or jig to fabricate. A simple, rough drawing made rapidly can communicate complex ideas very efficiently.
Does it have to be pretty? I'm not an artist.
Doesn't need to be art, but it must be clear and follow the basic rules.
Meaning?
It still needs to use conventional practices for lines, use dashed lines for hidden features, center lines where needed. It needs proper dimensioning if size is important. It needs to show the necessary views, orthographic usually, to fully describe the object or repair. A sloppy, non-standard sketch can cause just as much confusion as misreading a formal print.
Is there a standard process for making a sketch?
Yes, a logical flow. First, lightly block in the main shapes of the views you need using construction lines. Don't press hard.
Then add the details.
Add the details, still relatively lightly. Once you're happy with the shape and proportions, darken the final object outlines so they stand out.
Then dimension?
Then sketch in the necessary extension and dimension lines, again using the proper conventions. Finally, add any notes, the dimensions themselves, a simple title explaining what it is, and always, always date it and sign or initial it.
And if this sketch is actually going to be used to make a part, say for a repair?
Then it absolutely must provide all the necessary information. Material type, all required dimensions, all tolerances, finish requirements, everything needed for fabrication must be on that sketch. No guesswork allowed.
Okay. Sketches are important communication tools. What about other graphical aids? The sources mention nomograms and digital images.
Right. Nomograms are clever graphs. They usually show the relationship between 3 different variables or sets of data.
How do they work?
Typically, there are 3 scales side by side. If you know the values on any 2 of the scales, you can lay a straight edge across those 2 points and where it intersects the 3rd scale.
That gives you the value for the 3rd variable.
Exactly. The source example relates aviation fuel type, its specific weight density, and the temperature. Knowing the fuel type and temperature lets you find the precise density using the nomogram.
Why is that useful?
Crucial for things like fuel quantity indicator calibration. Fuel density changes significantly with temperature, which affects the volume to weight calculation the gauge relies on. The nomogram helps you apply the correct density value for accurate calibration. And often, critical notes are included right on the nomogram itself.
And finally, digital images. Pictures from cameras or phones.
Hugely important now. A clear digital photo is incredibly useful for evaluating damage, documenting conditions, sharing information about airworthiness issues like cracks or corrosion.
And they can be sent instantly.
Exactly. Transmitted globally in seconds for engineering review and disposition. Speeds up the whole process immensely.
Is there a right way to take these photos for maintenance records?
Absolutely. A best practice that turns a simple snapshot into valuable, measurable evidence whenever you photograph damage.
Put something in the picture for scale.
Yes. Place a measurement scale, a ruler, or even a common object like a coin right next to the damage. This immediately gives the viewer context for the size of the flaw.
And in the written report or email that goes with the photo.
You must state the exact location of the damage using the aircraft's coordinate system. Reference the fuselage station, FS, waterline, WL, and buttock line, BL. That way, the photo is unambiguously tied to a specific structural location in the aircraft's records. Hashtag tag tag outro.
Wow, okay. We have really covered the waterfront here. From the history, why drawings needed to be standardized, through the digital revolution with CAD and 3D models, all the way to the nitty-gritty of line types, sectional views, and even how to take a useful photo of damage.
It's a lot, but it's the fundamental language.
It really is.
Yeah.
And I think the key takeaway is that you're now equipped not just to, look at a drawing, but to actually read it, to see it as a precise set of technical instructions.
Instructions that directly translate to action.
Mm-hmm.
And the context has changed so much. The mechanics world used to be primarily about interpreting these fixed, static paper blueprints.
But now.
Now, with CAD designing the entire aircraft virtually, CAE simulating everything, CAM driving manufacturing, and technicians accessing dynamic 3D models and instantly sharing digital images, the whole documentation process is fluid. It's alive.
That speed, that fluidity,
Yeah.
it changes the responsibility too, doesn't it?
It absolutely does. It amplifies it. Think about it. Manufacturers design and simulate the whole aircraft digitally. Technicians on the floor can capture incredibly detailed, measurable images of damage with a mobile device. Images that tie directly back into that central digital record, referenced by precise coordinates.
So the technician isn't just a passive reader anymore.
Not at all. You're shifting from being just a reader of static plans to becoming an active, informed, and highly accountable contributor to that dynamic, living digital record of the aircraft's condition and history.
Which leads to a pretty critical thought for every AMT student listening.
Exactly. Given this power, this speed of digital information, how will you ensure that the digital references you consult, the measurements you take, the images you capture, are always unquestionably the source of truth? That accuracy, that diligence, that's the core responsibility of the modern aviation maintenance technician.